Last chapter, guys, nuclear chemistry. Now, nuclear reactions are not your standard bitch cop chemistry, and I can't do any nuclear reactions in the lab with you. I'm sorry, they won't let me build my own thermonuclear device or my own radiation center here. I don't know why, but they won't. So we're going to talk about nuclear reactions. And a nuclear reaction is one in which we see changes to the nucleus of the atom. Okay? Nuclear reactions do occur naturally, and we can induce them. There are man-made nuclear reactions, but there are also natural or naturally occurring nuclear reactions, and they're going on around you right now, and you're not aware of it. Okay? So let's remind ourselves about a few facts that we learned way back in the beginning of Chemistry 111. All atoms of an element have the same number of protons in the nucleus. That number of protons is called the atomic number, and it's given the symbol Z. But atoms of the same element can have different numbers of neutrons, which gives them a different atomic masses, okay? And gives them different atomic mass numbers. The atomic mass number is A, and it's the number of protons plus the number of neutrons. Atoms of the same element with different numbers of neutrons are called isotopes. Okay? Isotopes of the same element have the same chemical properties, but they have slight differences in their physical properties, like they're going to have different atomic masses. Okay? We call them isotopic masses. And their nuclei, their nucleus of the atom, is going to behave slightly differently. And that's what we're going to be looking at in this chapter. The differences in the behavior of their nuclei. Okay? Now, some words to add to our vocabulary. I know you don't want your vocabulary to grow anymore, but we just gotta. Okay? Nucleons. Particles found in the nucleus of an atom. So protons and neutrons as a group are considered nucleons. A nuclide refers to a nucleus of a specific combination of protons and neutrons. It's kind of a more generic term than isotope. Okay? So an isotope refers to atoms of the same element that have differing numbers of neutrons, but a nuclide is more generic. Now, in nuclear chemistry, we use isotope symbols a lot. The isotope symbol contains then the symbol of the element with a pre-superscript and pre-subscript. The atomic number is a pre-subscript. The atomic mass number is a pre-superscript. So things are going to be in the form A over Z, E, where E is the symbol of the element. So let me show you a couple of examples just to remind you. Okay? So that would be the isotopic symbol for carbon-14. Okay? Sometimes you also will see people write it like this, C-14, where they show the atomic number, and you're supposed to be able to look at the periodic table and get, atomic mass number. You're supposed to be able to look at the periodic table and get the atomic number. If I saw this guy, that's an isotope symbol, oxygen-17. Okay? So, isotope symbols. Now, let's travel back. In a neutral atom, the number of protons equal the number of electrons. A lot of nucleides are unstable, which means that they spontaneously undergo a nuclear change to form a more stable nuclide. Unstable nucleides then exhibit radioactivity. So guys, radioactivity is a spontaneous natural conversion of an unstable nuclide into a more stable nuclide. And radioactivity is out there in the environment whether man does anything or not. So radiation is out there. I hate to tell you this, but you're exposed to it every day. Very, 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 very minuscule amounts, but it's in our environment. Okay, it's not something we created, it's something we discovered. Undergoing nuclear decay, we have a nuclide of lower energy, and the excess energy is going to be carried away by emitted radiation and the recoiling nucleus. When it changes, it kind of expands and then contracts, and that recoil is what we're looking at there. So let's talk about the different types of radioactive decay things can undergo. The first one is an alpha decay. It involves the loss of an alpha particle. An alpha particle is made up of 2 protons and 2 neutrons and has a charge of +2. It's essentially the nucleus of a helium atom. Okay, the symbol for an alpha particle is the Greek lowercase alpha, pre-subscript 2, pre-superscript 4, because I have 2 protons, and this is its atomic mass number, which is protons plus neutrons, which is 4. Okay, so the parent atom then decreases its atomic number by 4 and its atomic mass number by 4 and its atomic number by 2 to form a new atom of a different element. Now, this is the one time in science where you see female language. The new element that's made is called the daughter. Yeah, it took nuclear chemistry to give us some female language. So, every element beyond bismuth atomic number 83 undergoes alpha decay. So let's look at a couple of examples. Okay, a classic example is uranium-238. The atomic number for uranium is 92. When it undergoes alpha decay, what I make is going to have an atomic mass number of 234, an atomic number of 90. If we look on the periodic table, okay, atomic number 90 is the element, should be the element thorium. Yep, TH. My purple's dying. Now guys, notice 234 plus 4 gives me 238. 90 plus 2 gives me 92. The atomic numbers on the 2 sides of the nuclear equation have to add up to be the same. The atomic mass numbers have to sum up to be the same on opposite sides of the reaction. So this is a nuclear reaction where we actually have a conversion of one element into another. Thorium, I got 2 dead puppies here. Let's see if my blue one works. Yes. Thorium-234, 90, is also bigger than bismuth, so it will also undergo an alpha decay. And so I get atomic mass number 230 and atomic number 88. Well, element number 88 is radium, Ra. Okay, so you can see alpha decay. Now, let's move on to our next type of decay, which is called beta decay. Okay, beta decay involves the ejection of a beta particle from the nucleus. The beta particle, okay, is a essentially high energy electron, okay, and it's formed from the decomposition of a nitrogen. Not a nitrogen, a neutron. So if you have an imbalance in the number of protons and neutrons in the nucleus and you have too many neutrons, a neutron actually undergoes a spontaneous change into a beta particle and a proton. Now, I want you to look at the symbols here. Neutron, has no charge, so its atomic number is 0. And there's one of it, its mass is 1, so it's got a mass number of 1. The beta particle has an atomic number here of -1 because it's a negative charge and a mass of 0. Okay? And a proton, 1 and 1. So if you look at it, 0 plus 1 gives me 1, a -1 plus 1 gives me 0. Okay? So, carbon-14 is the classic example of a particle that undergoes spontaneous beta decay. So, carbon-14 undergoes a beta decay. So the atomic mass number is still going to be 14, but the atomic number now is 7. That means the carbon has been changed into the nitrogen. This is going on in our environment all the time. If you've heard of carbon-14 dating, the amount of carbon-14 in living things remains constant over the course of their lifetime, because carbon-14 is being continuously made in the upper atmosphere because of radiation coming in from outer space. So as you consume plant matter or you take in carbon, your carbon-14 levels are going to stay the same if you're a plant or an animal. When that plant or animal dies, it stops taking in carbon-14, and the carbon-14 over time undergoes beta decay into nitrogen-14. So if you can determine the amount of carbon-14 in a sample and compare that to what it should be in a living sample, you can determine how old something is. Okay? It's kind of neat. Now there are limitations because, once the level gets down below a certain point, it's hard to detect. We'll talk about that later, but just previews. Okay? Now, let's talk positron. Okay? You may have heard of something called a PET scan, and PET scans are related to positron emission. A positron is an anti-beta particle, or sometimes called a positive beta particle, because it involves the emission of a particle that's the same size as a beta particle, but it's positive in charge, not negative in charge. Okay? So that's why it's called an antiparticle or an anti-electron. A positron is produced when a proton breaks up into a positron and a neutron. So a proton, 1, 1, breaks up into a positron, 0, 1, and a neutron, 1, 0. Okay? PET scans use positron emissions. Positrons, when they meet an electron, they annihilate each other and they give a burst of energy. And that's how a PET scan works. Now, let's look at an example here. Carbon-11 undergoes positron emission. Okay? And we get, when we have positron emission, I'm going to get 11 up here and 5 down here, so I get boron. Okay? Positron. Some people put a +1 here so that they kind of remind themselves that they're dealing with a positron. Okay? But that's a positron. Now, there are some situations where an electron can essentially be trapped in the nucleus. And this is called electron capture. It occurs when a nucleus interacts with an electron that's in that 1s orbit, so a low atomic energy orbit, and a proton actually fuses together with an electron, it slurps it up, and it becomes a neutron. So an electron capture, okay, what's happening is a proton is combining with an electron to give us a neutron. Iron 55 spontaneously undergoes electron capture. So iron 55 and iron's atomic number, sorry guys, I don't have this one memorized, 26. We do electron capture, and I'm going to get 55 here, and I get 25 here because a proton is turned into a neutron, and that means that it's turned into manganese. Okay, electron capture. Now, the last type of emission we need to talk about is a gamma emission. Gamma, notice, has an atomic number of 0 and an atomic mass number of 0. A gamma particle, quote unquote, okay, is a high energy photon that's exiting from an excited nucleus. Gamma photons come with other forms of emission. As the nucleus recoils after it spits out an alpha particle or a beta particle or a positron, as it's kind of reforming itself, it spits out energy in the form of gamma emission. Okay? So gamma emission comes with other things. And I'm not going to show you a reaction. So I've embedded a pretty table here. Alpha, beta, positron, electron capture, and gamma emission. So if we look here, you know, that kind of yellow halo, that's supposed to represent the fact that this is a recoiling nucleus, a nucleus that's been excited because of the change. And as it goes back to a stable form, it shoots out energy as gamma. Okay? All right, now, band valley of stability. There are two key factors to determine the stability of a nuclide, of a nucleus of an atom. The number of protons and the number of neutrons, essentially the ratio between neutrons and protons, so the N to Z ratio, is one of the most important, and the other one is the size of the nucleus altogether. Remember, everything over atomic number 83 is undergoing alpha decay. The nucleus is just too darn big to hold together. Okay? Now, let me talk for a moment about nuclear stability. We know that there are 4 basic forces in the universe. Something we call the strong force, something we call the weak force, something we call the electromagnetic force, and gravitational force. One of the big areas in study in physics is called grand unification theory. So they're trying to figure out how to pull all those 4 forces into a single force. Okay? They think that they might have figured out how to link strong force, weak force, and electromagnetic force. Gravity is the big sticker. But for right now, we're going to talk about 4 basic forces. And these 4 basic forces affect the stability of the nucleus. Really, for stability of the nucleus, we're most interested in the strong force and the weak force. Okay? And how the strong force and weak force play out depends on the size of the nucleus and the ratio of neutrons to protons. So if we look at page 901 in your book, okay, I'll eventually get to page 901, guys, don't worry. Page 901. I'm going to blow it up just a little bit. I think that's probably about as big as I can make it. Yeah. Now, the red line there is number of neutrons to number of protons being 1-to-1 ratio. Okay? When we're down here with 6 protons and 6 neutrons, down in that region, 1-to-1 is pretty good. But as the number of protons grows, and we have more proton-to-proton repulsion, okay, because they're light charged. Notice that to have a stable nuclei, you need more neutrons than protons. The little black dots here represent stable nuclides, okay? If you're above the stable dots or below the stable dots, you've got problems. You're going to undergo some kind of nuclear decay. Now, usually things up above the line have too many neutrons compared to protons. N's too high. So you're going to undergo beta decay. If you're down here, you've got too many protons compared to neutrons, you're either going to undergo positron decay, where a proton decomposes, or you're going to undergo electron capture to try to get to the magic dotted line. And if you are above 83, you're going to undergo alpha decay. So by looking where something falls on this kind of graph, I can tell you what kind of decay it's going to undergo. The yellow, okay, here represents known nuclei, kind of their regions. The black dots represent stable nuclei. Okay? Now, here's another version of this. I like this one a little better because it spells it out. Beta decay up above, positron emission or electron capture below. And it does a blow up here. The black dots are stable, and there's, a beta decay moving toward a stable. There's a positron emission. So I might have this one move, we have movement toward, so there's an alpha decay, there's a beta decay, there's an electron capture, so that we can see all the different ways that we can move in to be a more stable nuclei. That's buried in your notes, so you can use that or the one in your textbook. Okay? So, 2 major forces that play a role in stability, strong force and the weak force. The strong force is an attractive force that exists between all nucleons. It holds them together. It operates over a very short distance. The balance between this force and the electrostatic repulsions between protons greatly affects the stability of the nucleus. Might lead us to believe that adding in more neutrons might be the solution for a more stable nucleus, and this is the approach they took when they were trying to make heavier nuclei in the beginning to try to see if we could manufacture changes to the nucleus of the atom. They just tried sticking extra neutrons in. By the way, that's how we accidentally split the first atom. What we've discovered, or what it looks like, is just like there are energy levels for electrons inside the atom, there are energy levels for protons and neutrons in the atoms. That means that when we add neutrons, sometimes we have to open up new energy levels of higher value. And there's a breaking point between adding in these neutrons to reduce the positive repulsions and the energy levels. So the strong force, one of the 4 basic forces in nature, okay? As the name implies, it's really strong. It's the strongest of the 4, but it has a very short range. Gravity has the longest range. meaning the particles must be extremely close together before any effect is felt. Its main job is to hold together the subatomic particles of the nucleus. Protons, which carry a positive charge, neutrons, no charge. These particles are collectively the nucleons. As most people learn in science, like charges repel and unlike charges attract. Okay, so the neutrons are in there to help with that repulsion. So positive, positive repulse, negative, negative pulse, positive, negative attract. If you consider that the nucleus of the atom, except for hydrogen, contains more than one proton, then the protons carry positive charge, they repel each other. The reason that they stick together is because of the strong force, attractions between neutrons and protons and protons. Okay? We talk about them doing an exchange of a particle called a meson, which kind of ping-pongs back and forth between these particles. Okay? Now, you guys can read all about mesons. The strong force is too weak to make them sit together if they're too far apart. They're too far apart to exchange mesons. Scrolling up. So when a nucleon approaches another nucleon, it has to get past that electrostatic kind of barrier to be able to stick and to exchange nucleons. Now you guys can read this. I'm not going to bore you by reading it all to you. Okay? Okay. When the nuclei are too large, the strong force can't hold them together, which means the electrostatic repulsions are too great, and the nucleus actually blows itself apart, and we see alpha decay. So, nucleons that have too many neutrons above the valley of stability undergo negative beta decay, which depends on what's called the weak force. Now, let me show you a little video on the weak force. It's a cute one, you'll like it. Okay, come on, let me look at my files. Why doesn't this computer have a file? You know what? I hate this computer because I should be able documents. Go documents. Okay, this computer won't let me play it. Guys, I'm sorry, but this stupid computer won't let me play the file for you. I'll send you guys a link and an announcement, okay? So that you can watch the short video on the weak force. It's really neat. I think it would be worth your while to watch. Okay, if the NZ ratio is too low, too few neutrons in the nucleus, you see positron emission because you've got to get a increase in the number of neutrons and a decrease in the number of protons. So if we look at practice problem 20.3, okay, on page 902. Okay. It says, predict whether each nuclide is most likely to decay via beta decay or positron emission. So we're looking at lead 192, lead 212, and xenon 114. So I'm going to write those down, okay? Lead 192, lead 212, and xenon 114. Now, guys, what they're asking us to do is to think about the proton to neutron ratio. So let me pull up the atomic numbers here. Okay, the atomic number for lead is 82. And the atomic number for xenon, okay, is 54. So, for each one of these, I'm going to get the number of protons and the number of neutrons. So let's do that first. 192 minus 82 gives me 110 here. 212 minus 82 gives me 130 here. And xenon protons 54, and 114 minus 54 gives me 60. Okay? So I have the number of protons, I have the number of neutrons. Now let's go back and look at that chart. Okay? Okay, guys. So if I'm looking at lead, which has an atomic number of 82, so 50, 60, 70, 82. We're way out here near the end, okay? And 110 is here, 82 is here. I'm in this region. If I'm in this region, I am in positron emission or electron capture. So for lead 192, we'd expect positron emission. Don't worry, I'm going to show you where I've written all the answers in a second. With lead 212, okay, where we have 130 neutrons, so if I come out here to 82 and I'm looking at 130, I'm right in here, okay? That means that I'm on the beta decay side of things. Now, the last one we had was xenon, which is atomic number 54, so it's 10, 20, 30, 40, 54, and 60. 54 and 60, right about there. If I'm right about there, I'm underneath the line of stability, so we're talking positron emission. Okay, so when they ask you to determine what type of decay something's going to undergo, what you're going to do is you're going to figure out how many protons and how many neutrons. Then you're going to go to this chart of stability, and you're going to locate those two on the chart so you can decide what region they're in and what kind of decay it's going to undergo. All right. Now, keep scrolling. Now, when looking at the energy shells for protons and neutrons, there appears to be a quantum mechanical energy shell arrangement for the nucleons, just like there are for electrons, where pairs are much more stable than singles, so even numbers are better than odd numbers. Turns out that when we look at stable nuclides, and here's an example of some nuclides. You see their atomic number. Cadmium's atomic number is 48. There are 8 stable isotopes, nuclides of cadmium, that are stable. Whereas you look at iodine, which has an atomic number of 53, so it has an odd number of protons, there's only 1 stable nuclide. Okay, scroll up. Okay, if we look at odds and evens, stable nuclides that have an even number of protons and even number of neutrons, 157, even protons, odd neutrons, 53, odd number of protons, even number of neutrons, 50, odd, there's only 7. So we know of 267 stable nuclides. And notice most of them involve having evens. And having even protons and even neutrons is the best. Okay? Nuclides are much more stable if the number of protons and number of neutrons is even. But just like noble gases, we have what are referred to sometimes as the magic number. 2, 10, 18, 36, 54, 86. If you have that number of protons or that number of neutrons, they're extremely stable. Okay? Those were the number of electrons that we find in noble gases. Okay? So, they're sometimes referred to as the magic numbers. Radioactive decay of any type, okay, is a first order process. So it means the rate of the chemical reaction, okay, is a first order process, which means that the half-life is independent of the amount of starting material. So the half-life, the time needed for half of the sample to undergo decay, T1/2, is the natural log of 2 over K. Different materials have different half-lives. I'm not going to make you do any calculations of half-lives. We've already done that. We beat it to death at the beginning of the semester. But I just want you to remember what a half-life is. So here's some examples for beryllium isotopes. You can see that they can have half-lives of, fractions of a second up to thousands of years, depending on what the isotope is. Okay? Radiocarbon dating uses radioactive carbon-14 isotopes to determine the age of something by measuring the percent of carbon that is carbon-14 in the material and compare it to the amount of carbon in living things of the same type. Carbon-14 dating is good for about 36,000 years, although I've looked up some sources and says that they're now pretty confident using carbon-14 dating up to 50,000 years. Anything over 50,000 years in age, you can't do radiocarbon dating. Let's see, table, page 904. Okay, if we want to deal with anything older than 50,000 years, we have to look at some different isotopes. They look at thorium, uranium, to do some dating if we're looking at things older than 50,000 years. Okay? The half-life of carbon-14 is 5,715 years. Notice uranium's 4.5 times 10 to the 9 years. Thorium is 1.4 times 10 to the 10 years. So they look at things like radioactive thorium, radioactive uranium, if they're doing things like dinosaur bone dating. Okay? All right. Moving on. Now, actually, guys, that is a good place to stop. I will pick it up there on the next lecture. My battery's just about dead.